So this lecture is going to be about activation functions. Activation functions. So what are activation functions and why do we need activation functions in a network? Now think about it this way, a very simple example, although you cannot compare how we are neurophysiologically organized as human beings and how things how we look at nonlinearity when we look at activation functions. But let's say if you had a bunch of blocks, straight blocks, and you wanted to actually fit these blocks in a curve. Now, ideally, you would want these blocks, and let me just kind of put these blocks this way, and you would want to connect these blocks, just like a little chuk-chuk train you would want to have, with some kind of a junction where, an activation function could be something that is connecting these blocks here, 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 and essentially, connecting, so here, so it's connecting here. So you get the idea. So basically, you will not be able to fit these rectangular blocks if you didn't have some kind of a connection. It'll just kind of hit straight across this curved line. And your whole idea is to fit these blocks into this curve. So that's the whole idea. You want to do this. So essentially what we are trying to do is you want to create some kind of a connection or some kind of a coupling or some junction at these places to make sure that these guys are connected to the activation, connected to each other, and they fit the non-linearity. So, just to give another example of what I mean about non-linearity, if you were to linearly, let's say you have three inputs. We can say x1 is one input, x2 is another input, x3 is another input, and then you have, let's say, a bunch of nodes. So n1, n2, n3, n4, n5. I always miss this, I don't know. N5. And then you have an output neuron. Let's call it just N7. And essentially, so if it was a fully connected layer, it would be like this. Let's make it fully connected, just for the sake of the example. And connect this as well. And this guy, and eventually outputting here. Then, this is a fully connected, so you could say this is a fully connected layer, essentially a dense network, they're all connected to each other. And now if you were to look at this is basically, if you just do a linear operation, let's say, just pick one, x1, x2, x3, piece by piece, right? So, and then we have our n1, and we have n1, and you could assign some values here. So the weight here is 1, let's say the weight here is 3, and the weight here is 5. And then similarly you can look at, again, x1, x2, x3 for the second node. It looks like this. Just need to make sure the colors are all okay. And here you have similarly weights, some weights 2, 5, 7, let's just say. And this way, you can go on and on. And essentially, if you look at the output neuron, which is this guy is your output neuron. And if you were to have all these multiplications and additions, and if you came to this output neuron value, let's say the value is, don't need to go into the details. Let's say the value were to be collapsed in directly to this output neuron, which is N7, and if it were x1, x2, x3, the input values, and let's say it's 57, x2 is 7, and x3 is 69 or something, and then you're on to your N7. So essentially, we are trying to say that, this whole addition and multiplication that we did here, and it doesn't matter, we just take these values and essentially collapse. We collapse this all into the output neuron, which is this. What you're going to find is the values that you did if you were to do this whole operation, so this whole additions and multiplications that you did, essentially the linear operation, is same as if you didn't actually even had to use all these internal nodes. So basically the values of doing the additions and the multiplications and coming to this value of the output neuron N7 would be same as if you in fact even didn't need to have this and directly applied those values. You would get the same value. So basically that's great, right? So we just need one neuron to be able to do that operation. It all sounds fantastic. It's wonderful. But actually that is really a problem, because you are not going to be able to solve complex problems that you have in your neural network by just collapsing into one neuron. It's just not, let's say, robust enough for you to do that. So an activation function is actually, essentially, it's more than that. The whole idea, the purpose of the activation function is, so what is the purpose? So activation function's key purpose is to avoid network collapse. So your network doesn't collapse. And the second is, doing just the applications of multiplications and additions, which is linear. You're actually doing a nonlinear operation. So it's a non-linear operation, right? Just as we kind of drew here in this example, as you see here, the whole idea is to have this nonlinearity, so you're able to essentially, fit the curve. And it's also sometimes called nonlinearity. So an activation function is also called, sometimes it's also called transfer function, and is also, called nonlinearity. So I guess what I'm trying to say is that your activation function is, it's an operation that makes a floating point number as an input and returns a non-floating point number as an output. So we're going to go and look into various activation functions. We're going to go and look into activation functions like LU, ReLU, max out, soft, plus, dan-h, and there are a few. Obviously, then you have the LU guys have a bunch of other families. You can see, so LU, you have many guys, and LU, you have leaky, ReLU, I meant this, my apologies. Then you have shifted ReLU and more. So I'll be talking about these in the next bunch of series, and I hope to see you guys in the next class.